So this video is about swapping out this old clock we've kept on our fireplace mantle for something a little more attractive. To that end, we found this pretty little piece on Amazon and ordered one. But what my wife didn't know was, what she thought was just a clock replacement, I, as a gadget kind of guy, saw an opportunity for a project. So this is what we eventually ended up with. Now you might be asking, what would be the purpose of having two clocks? Well, actually, only the one on the left is still a clock. So what's the one on the right? See a difference? If you notice that there's only the minute hand, you would be right. So here you get a much closer view, and if you've guessed this one is now a temperature gauge, you would be right again. Not an indoor temperature gauge, but an outdoor temperature gauge. Also, I photoshopped the original clock face using the same font and coloring as the original. Keep watching to see how the clock was transformed into an outdoor temperature gauge. Looking at the back side of the clock. At 5, I ran 5 volts to the back, but because I swapped out the original lighting for an LED strip that is always on, more on that later, I found I only needed about 2.5 volts for that LED lighting. That's the reason for the buck converter at 2. Then at 4, I ran 5 volts, 2.5 volts, and ground over to the temperature gauge. Looking at the back side of the temperature gauge, you can see a stepper motor and its controller at 1 and 2. If you don't know what a stepper motor is, it's an electric motor that you can precisely control how much or how little rotation is required. In this application, and after some simple calculations, I determined I wanted it to rotate exactly 17.5 degrees on the compass for every 1 degree of temperature change. At 4, I show the ESP32 microprocessor that receives the current outside air temperature from a sending ESP32 out in our backyard under a tree. One consideration when using a stepper motor is that they consume electric power all the time, even if they're not rotating, and that means they get hot unless, as in the case here, every time the temperature changes, power is turned on, rotation is commanded, and power is turned off. Microprocessors like the ESP32 can't handle the amount of current required to rotate a stepper motor, but they can control switching devices that can provide the required current. Enter the MOSFET. At 3, I show a MOSFET. Let's take a closer look. For comparison purposes, I show a relay and a MOSFET, both of which can act as a switch in an application like this, but obviously the MOSFET takes a lot less real estate and in this application much simpler to use. To oversimplify, if you apply a small amount of current from the ESP32 to the leftmost pin, it has the effect of connecting the other 2 pins. In this way, power to the stepper motor is turned on and off. Now let's take a look inside of that same temperature gauge backplate. Here I show how the gauge is calibrated whenever there's a loss of power. When power is restored, there's no way to know where the needle is pointing. So the ESP32 commands the motor to rotate counterclockwise until the sensor at 1 senses the magnet at 2. The needle is attached to the shaft at 3 such that now it points to 70 degrees. Then this ESP32 begins listening to the sending ESP32 and moves the needle accordingly. Now let's see how the lighting was changed. Shown here is the original lighting. It is turned on manually by pressing a small switch on the back. This is acceptable given the price point and the fact that it is battery powered, but doesn't work at all for this application. Enter this very nice little flexible Cobb LED light strip. It's rated for 5 volts, but that was way too bright for this application. I found I could take it down to 2.5 volts before it shut off. In the event, that worked just fine, as you can see here. The light strip provides an attractive border and the entire face is evenly lit up. Up until now, I've only briefly talked about the sending ESP32. Here's where it lives, under a tree in our backyard. The ESP32 has a feature known as ESP Now, which allows them to communicate wirelessly. No other hardware is required. In this application, I'm using the one on the left to read the temperature from a sensor and transmit it to the receiving ESP32 on the mantle. Shown here is the temperature sensor as received. At 1, I show the buck converter, which reduces the available 12 volts from another existing and unrelated project to 5 volts. The sensor must be powered by 5 volts, and the ESP32 can be powered by 5 volts. I separated the actual sensor from its PCB in an effort to keep it out of the weather. I had a small funnel in my junk box that I used as a poor man's rain cover. In closing, the front side of the temperature gauge backplate is shown in action during power-up testing. Once power is restored, the needle is rotated counterclockwise until the magnet is found. Then it starts receiving temperature values from the sending ESP32 until the actual outside temperature is reached. After that, anytime there is a temperature change, the new value is sent and the needle is moved accordingly. Last, the front of the gauge is also shown during power-up after the project was completed.